We're going to go through 3.6 on heating and cooling curves, looking at our heat outcome, analyzing qualitatively and quantitatively the effect of heat on matter during temperature changes and changes of state using kinetic molecular theory. We are going to be looking at how to calculate the quantity of heat using the latent heat of fusion and the latent heat of vaporization to the correct number of significant figures, and to construct heating or cooling curves for water and other substances. So remembering there's three main states of matter, or solid, liquid, and gas, and all matter has energy unless it's at absolute zero. But different states of matter have different amounts of kinetic energy. In a solid, the particles have kinetic energy and they just vibrate. They're strong forces that hold particles in place. They can only really vibrate back and forth and cannot slip past each other. And therefore, solids can just really only hold their shape. Versus the liquid, our particles have more energy. They're still very tightly packed, although they're able to slip past each other, which, as a result, liquids are able to flow. And gas particles have even more energy. They are still attracted to each other, and they're able to move around much more freely from place to place. Gases are able to flow, and because our gas particles are so much more spread out, you can compress our gases into a smaller container. A few different definitions here. We have melting, which is the change of state from a solid to a liquid. Fusion, which is the change of state from a liquid to a solid, sometimes called freezing. Vaporization is the change of state from a liquid to a gas, sometimes called boiling. Condensation is the change of state from a gas to a liquid. Sublimation is the change of state from a solid to a gas without being in a liquid phase. So if you think about dry ice, that goes from solid carbon dioxide to gaseous carbon dioxide. And deposition is the change of state from a gas to a solid in one step. Now, since our particles and substances in different states have different amounts of energy, heat must be added or removed in order for substances to change state. Melting, vaporization, and sublimation all require energy to be added, and therefore they are endothermic processes. Fusion, condensation, and deposition all require energy to be removed. Therefore, these are endothermic processes. They give off heat. If we think about ice, if we start with ice and we heat it up to 0 degrees Celsius, it's going to begin to melt. And it's going to continue to melt until all of the ice is gone, and then it's all water. And then if we keep heating it up, our water will heat up until it's 100 degrees Celsius, and then it's going to start to boil. Now, if we captured all the gas and put this in like a little closed box, this water would keep on boiling until there's no more water left, and that water is going to stay at 100 degrees Celsius until it all becomes gas or steam. And once all of our water is steam, then the steam will continue to heat up above 100 degrees. So the reason for this is that 100 degrees Celsius is the boiling point of water, or the condensation point. It's where it changes from a liquid to a gas. And all of the energy you're adding will now go into changing the state of particles, and the water will stay at 100 degrees Celsius until it's all a gas. And once the water has turned entirely to steam, again, if you continue to add energy, the temperature will start to rise again and the steam gets hotter. So if we look here, we can create a heating and cooling curve or graph. Time is on the bottom, and temperature is our axis on the side here. If we start, say this is the heating and cooling curve of water, maybe we start, maybe it's a cold day, we have some ice outside, it's minus 30 degrees. We bring our block of ice in and put it on the stove and heat it up. Once it reaches 0 degrees, it's going to start melting, and it's going to take some time. If we take a look here, it's going to take some time for our ice water mixture to completely turn. So this is going to be all water now, right? And this, at the beginning, this would have been mostly ice, little water. And then our water will then heat up until, so our water is then going to heat up until it's at 100 degrees Celsius. That takes some time. Once it's at 100 degrees Celsius, it's going to boil. And it'll take a while to boil all the water away. And once all the water's boiled away, if we captured all that gas, that steam, then we would see that our steam then heats up above 100 degrees. So this temperature right here would have been 100 degrees that our water starts to boil. So if we draw a heating or cooling curve for water, if it starts at ice at 32 degrees and warms to steam with a temperature of 120 degrees Celsius, so we need to make sure we draw an axis here. We have time on one axis and temperature. On our y-axis. And we're starting at negative 32 degrees, so we'll say at the bottom we have negative 32 degrees Celsius. Our water, which is negative 32 degrees Celsius, is ice. It's going to heat up until it reaches 0 degrees. And then once it's at 0 degrees Celsius, it's going to melt and take some time to melt. And then once it's all melted, it's going to heat up to 100 degrees Celsius, where it then boils and takes some time to boil. And then it will heat up to, as steam, to 120 degrees Celsius. So sometimes I find this helpful to write in, right? We have ice, and then water, and steam. And then on our horizontal parts, that's that phase change part on our graph, so where it goes from ice to water. So this is melting, right? And you got boiling. And if we can also draw another cooling curve, so we drew a heating curve. Now we can draw a cooling curve for water if it starts as water at 40 degrees Celsius and cools to ice with a temperature of negative 13 degrees Celsius. So we draw our graph. Maybe we should draw a little straighter than that. We have time and temperature. And it starts at 40 degrees Celsius and it cools. So now we're going to have to start relatively high at 40 degrees Celsius. And it's going to start cooling down. Now we have water at 40 degrees Celsius, and it's going to stay water and stay cooling down until it is at 0 degrees Celsius, which then, at 0 degrees Celsius, here I'm going to change colors. Here, just so I don't confuse you. and make it a little more clear. So it cools down until 0 degrees Celsius. And at 0 degrees Celsius, it undergoes that phase change where it freezes into ice, and then it's going to cool down until negative 13 degrees Celsius. Now these numbers on the side and the kind of the scale on the side, I just really am looking for a good estimation. I'm not going to go and measure it. I just want it to be a really good idea of what is happening, but not necessarily drawn crazy to scale. So I'm going to write in again what's happening here. We have our water, it's cooling down, and then it's freezing and turns into ice. Okay. So some important notes here is that although it's simple, to keep it simple, the graph has perfectly straight lines. It's not unusual for the graph to be curved. When you kind of have that ice-water mixture, it might go slightly above or below 0 degrees if you were actually reading it with a temperature probe. And every substance has its own freezing, melting, or boiling condensation points. Right, if we're talking about the boiling point of alcohol, the boiling point of alcohol is significantly lower than water. It's 80 degrees Celsius. Or if we're talking about, I think its freezing point is significantly lower too. Not sure off the top of my head. It is significantly lower, but I don't know what the number is off the top of my head. And then something like like lead would have a relatively high melting point, right? Just at room temperature, lead is a solid, and it's going to, you need to heat it up quite a bit in order for it to melt. And different conditions can change freezing and boiling points of a substance. The two most common are pressure and presence of a solute. Most relatable is like water. If we talk about boiling a pot of water on top of Mount Everest, it would boil a lot sooner because it has way less pressure. Or if you put, that's also the reason why we put salt in water, because salt lowers the boiling point of water. And under certain conditions, substance can be in a different state than when they should be at a certain temperature. Supercooled liquids are the most common seen example. If you've ever had like a water bottle that hasn't been opened, like a plastic water bottle that hasn't been opened in your vehicle, you left it in your vehicle. I don't know if you've seen this, or you might want to YouTube it. You can, you have in your vehicle or on a cold winter's day, and then you take it out of your vehicle, or you pick it up and you're like, what the heck, it's still water, it should have froze. And then you crack it open and then release the pressure, and it immediately turns into ice. So that, in that case, that would have been a super cooled liquid, still in the liquid state, but it just didn't have kind of a nucleation point, is what they call it, to turn to ice. And once you release the pressure, it allows it to turn to ice. And sometimes substances can change between solid and gas phase without being in the liquid phase. So a new formula here. So we can calculate the amount of energy needed to change the temperature of a substance. We can also calculate the amount of energy required to change the state of a substance. We can use this using the idea of latent heat. So the formula for latent heat is Q is equal to mL. This is when you're changing that state of a substance. So if we look back on our lovely heating and cooling curve, so this cooling curve here, we would use this Q is equal to mL formula whenever we change state. So that's that horizontal line point, is when we change state. And whenever we have that change in temperature, we learned a few lessons ago, we can use Q is equal to mc delta T. So we have a change in temperature, right? We don't have a change in temperature when we're changing state, but it still does take energy put in to change the state of a substance. And then whenever we have like line that isn't completely horizontal, and it is changing temperature, we need to use our specific heat equation. So we have Q, which is the latent heat of energy, measured in joules or kilojoules, depending on your table. Your M is your mass in kilograms, which also could be in grams. Just need to make sure you match it to your table, again, just like specific heat. And L is the latent heat of fusion or vaporization. There's a note on the bottom. It says solid heat of fusion is when you have a solid to a liquid, or like vice versa. And use our heat of vaporization value if we're going from a liquid to a gas, or vice versa. And you need to remember to be careful with your positive or negative sign. Because there is no change in temperature, it mathematically doesn't give you a negative value when you calculate your latent heat. Now if we take a look at our cooling curve, this would be giving off heat in order to cool water, which is exothermic, which means we should have a negative Q value, right? So this is an exothermic process, which means Q needs to be negative. So we would calculate Q is equal to ml, and it would come out with a positive value. We need to make sure in joules or kilojoules, we need to make sure we would write in our negative value. Whereas when we use our specific heat formula, it's actually just going to calculate with a negative value already because of that temperature change in our equation. So we just need to watch for that. Our latent heat table, so there's many latent heat tables. Here's one, right? So we have and a few examples of our melting and boiling points here. We have helium with a melting point of negative 269.65 degrees Celsius and a boiling point of just slightly higher, actually. We can have oxygen with a melting point of negative 218, right? Or if we go further, I was talking about lead has a melting point of 327.3 degrees Celsius, and it will boil actually at 1,750 degrees Celsius. Okay. So our first example here is how much energy is required when 250 grams of lead melts. With these questions, I find it best to make a graph to kind of show what's happening here. So we're looking for lead melting, and when we're talking about something melting, it doesn't give us a temperature, it's just changing state, right? That's that horizontal line when it's just changing state. So this one's not a very exciting graph to draw, and we don't know what temperature it is, which is fine because we don't need that. We just need to figure out, it should be time on the bottom. Time and temperature on the side. We just need to figure out how much energy is required in that change of state. And remember, whenever we have that horizontal line or that change in state, we need to use Q is equal to mL. When it's talking about lead melting, melting means we need to use our heat of fusion value because it's changing from a solid to a liquid. So we can look at our table, and if we take a look at our table lists that we have the units for our heat of fusion are in kilojoules per kilogram. So our mass needs to be in kilograms. We can change that, so 0.25 kilograms, and then we look up our heat of fusion value for lead, which is 20.4. And remember, that's kilojoules per kilogram, meaning that our units for our final units we're going to have for our energy are going to be in kilojoules in this case. So if we multiply 0.25 by 20.4, we get 5.1 kilojoules. And that's to proper significant figures. If we take a look at this lovely example here, how much energy is required when 1.5 kilograms of water turns to steam? Again, we draw our lovely little graph. It says 1.5 kilograms of water turns to steam. We are just doing a phase change here. So that's just that horizontal line. We got time and temperature. And whenever we're talking about that phase change, we know we need to use Q is equal to mL. So Q is equal to our mass in kilojoules, which is good, times L. Our water is turning into steam, which means we need to use our heat of vaporization value of water. It is 2,260. So Q, if we plug this into our calculator, 1.5 times 2260, we get 3,390 kilojoules. Now that's not to proper significant figures, so let's change that out. 3,400 kilojoules. Good. All right, we have a slightly different question. How much energy is required when 1.5 kilograms of 20-degree water turns to steam? So we know at 20 degrees, that water is going to need to heat up to 100 degrees in order to turn into steam. So let's draw what's happening. We have our time and our temperature. That water's starting at 20 degrees. And it's going to have to heat up to 100 degrees in order to start turning into steam. So our water starts at 20 degrees, heats up to 100, and then takes some time and turns into steam. So now if we take a look at this, we have two different scenarios happening. We have a phase change and kind of a change in temperature. So we need to use two different equations here. Remember, whenever we have that change in temperature, or section 1 there, we need to use Q is equal to mc delta T, our specific heat formula, because we have that change in temperature. Well, Q is equal to 1.5, and it's the specific heat of water, right? Because at 20 degrees we have water. If we were talking about under 0 degrees, we would have to look up the specific heat capacity of ice, or above 100 degrees, it'd have to be of steam, because all those have different values. So water has a value of 4180, and then the change in temperature, if we take a look here, it's starting at 20 degrees, and it's ending, or our final temperature is at 100 degrees. So we have 100 minus 20. Okay. So Q is equal to, which is 80 degrees. And we multiply those numbers together. So Q is equal to 1.5 times 4180 times 80. We get 501,600. Our answer is in joules, because remember, specific heat capacity is in joules per kilogram degree Celsius. And then we need to do a second formula for Q is for our phase change, which is Q is equal to mL. water turning into steam is our heat of vaporization. We go 1.5 times heat of vaporization of water is 2260. So Q is equal to 1.5 times 2260, which is 3390. This is kilojoules. And then in order to add both of these values together, we need to have the exact same units. So I might convert joules to kilojoules. We have 501.6 kilojoules. And then I can add both those values together to get the total energy required. So 5, I want to say like Q total is equal to 501.6 plus 3390. So Q total is going to end up equaling to one significant figure, which will be 4,000 kilojoules. There we go. And last question, longest question. We are going to look at 2.30 kilograms of ice at negative 15 degrees Celsius is warmed until it evaporates into steam at 135 degrees Celsius. So we need to sketch a temperature versus time graph of this process and figure out the total amount of heat required for this to occur. Let's take a look at this. We got time, temperature, and it's starting at negative 15 degrees Celsius. And if it's starting at negative 15 degrees Celsius as ice, it's going to heat up to 0 degrees Celsius, where it melts, and it turns to water. And then once it melts and turns to water, it has to heat up to 100 degrees Celsius, where it's going to boil. And turn to steam, and then goes to 135. So it's 100 right over here, 35 degrees Celsius. So if we remember, we have our first phase change is melting, so we need to use our heat of fusion value. We have our heat of vaporization value we're going to need to use for our second phase change. We have our substances ice in our first section, water in our second section, and steam in our third section. So if we want to label those, that's helpful. We have 1, 2, 3, 4, 5. So 5 different calculations for this beast of a question. We'll get through it. So number 1. We have that change in temperature, so we need to use Q is equal to MC delta T. Q is equal to, our mass is 2.3 times the specific heat of ice. So be careful there. Specific heat of ice, look that up. That is 2100. And our change in temperature, it initially is negative 15. It's finally 0. 0 minus negative 15. Okay, so we plug that in. Let's figure out that value. So 2.3 times 2100 times 15. We get 72450. And remember, this is in joules, and let's convert it to kilojoules because we know we're going to have to add them up in the end. All right, number 2. Q is equal to ml because it's a phase change. And because it's going from solid to a liquid, we need to use our heat of fusion. So 2.3 times our heat of fusion value for water, which is 334. So Q is equal to, do this on our calculator, 2.3 times 334. 768.2 kilojoules. All right, number 3. Q is equal to mc delta T because we have a change in temperature. So Q is equal to 2.3, and our substance is water, so it's 4180. Our change in temperature initially is 0, final is 100, so we go 100. Q is equal to 2.3 times 4180 times 100. We got 961,400 joules, which, changing to kilojoules, 961.4 kilojoules. All right, we're getting there. Number 4. Q is equal to ml. We have our heat of vaporization value we need. So Q is equal to 2.3 times our heat of vaporization value, which is 2260. And Q is equal to 2.3 times 2260. Wrong thing on my calculator. 5198 kilojoules. And number 4. Number 5. It's a good thing I messed up on that because I'm going to have to switch where I'm writing this. Oh, I'm running out of room. 5. Q is equal to mc delta T. Q is equal to 2.3. And now this is steam. You can take a look for the value for steam, which is 2,000. And then it's starting at 100, going to 135. So 135 minus 100. So Q, if we work this out, we have 2.3 times 2,000 times 35. We subtract that. I'm just going to divide by 1,000 right now to change into kilojoules because I'm running out of space. 161 kilojoules. And then the total, right at the top here, Q total is equal to 72.45 plus 768.2 plus 961.4 plus 5198 plus 161. And Q total is equal to, oh my gosh, this will probably be the longest question you'll have in Physical Science 20. It definitely is the longest question you'll have in Physical Science 20. But not super hard, just time consuming. Maybe it is hard. That's okay, too. Just make sure you show as much work as you can, all your steps, and I try to give you as many marks as I can. 7,161.05 kilojoules. And all normally on a test I would tell you to write a certain amount of significant figures. We're just going to write this to 3 significant figures. So 7,160 kilojoules. And here's our final answer. There we go. Long lesson today. Sorry about that. Let me know if you have questions.